Recording begins. It is December 5th, 2025, and this is ESM 105. What do you got going on this week? It's the second to last week of classes. It's Friday. The one big thing you got is the annotated bibliography due. End of the day Sunday, right? So get that in by 11:59 p.m. on December 7th. Please. Yeah. That'd be great. Next Sunday, you'll have quiz 6 due. Then the final exam is open on Wednesday. It's available from 8 until 2 p.m. You get 2 hours to do it, 120 minutes to do it. It's got 25 questions drawn from the quizzes that you've done all semester, okay? So each quiz is set up as a question bank, and there are 6 different question groups, and I have it randomly draw 4 to 5 from each group based on, most of them get 4, one of them gets 5, to make it be the right number of questions. Any questions about that? Awesome. So please just make sure you start it by noon so that you have the full 2 hours to do it. Okay. In that case, let's just go ahead and get back into our course material. We're wrapping up the week 12 through 13 pollution talk, and then we'll get into agriculture and a bunch of talk about water. Water's important. Alrighty. So last time we ended with Superfund sites and what is the Superfund, and how the Superfund funding has been really ankled by changes to where the money comes from, loss of that polluter's pay tax, okay, which involved a tax on chemical, petroleum, corporate income above $2 million. That was a huge source of revenue to fund Superfund projects. That goes away in 95. This polluter's pay tax gets reintroduced in 2021, but with the corporate tax piece removed and the petroleum piece removed. So industries that still fall under chemical companies still had to pay an increased tax for Superfund projects, but it just was a massive reduction in money. So now what we have are a lot of Superfund sites. We went through the Love Canal story. Now we have a lot of Superfund sites that are sitting there. They're on the project list, the national project list, and they're waiting to be addressed. Here in Humboldt County, we have 2 Superfund sites, one of which is active and is in the investigation stage. That's the Copper Bluff Mine in Hoopa, which is right next to a river, and so, there's some concerns. It's from an old mining operation. And then the removed one being the Keltor Chemical Works project, also in Hoopa, okay? Yes? It's not in the Superfund list. So it may have had an assessment done, but I'm not sure why it is not on there. Yeah. It could be that containment has been considered to be sufficient, Containment is now identified as, that was one of the modifications to environmental protection laws, was including containment as a viable way to treat hazardous waste. So if I had to guess, that would be what my guess would be. Solid. So remember, one of the things about these regulations is that even after the fact, companies and the responsible parties could be held accountable for the damage caused by these projects. So the EPA was able to recover a significant amount of, some money from a single operator at this chemical works, but this project was incredibly expensive. Here's we talked about brownfields, good. Here's what the project sort of looked like. Small area here at this bend in the river, okay? Some really good cleanup work. Testing has shown that it seems to be clean now. This is stuff that we've all sort of talked about. I'm kind of glossing over the last couple slides, so maybe I'll just really briefly hit these, all right? In fact, this sort of talks about what we were talking about. storing waste permanently, containment as a viable option, secure landfills with lots of testing systems for making sure that nothing's seeping out of the area, capturing mechanisms for capturing, methane and gases like that. Monitoring under drains. All right, so you just take the hazardous waste and you store it. That's one management option. And if we're using cradle to grave principles, then the industries which generated the waste should be the ones responsible for maintaining these storage facilities. But a constant issue we run into with this is the companies becoming different companies. And now I'm not that company anymore, So I don't have to pay for it. It's not my waste anymore. That was the other guy. Yeah. Okay, cool. Not cool, but this is fine. We've talked about this already, and I love it. I don't love it. Here we go. So this is the last few slides here from this PowerPoint, which is just taken directly from the EPA site. All right. It has to do with, it was a presentation given to update people on the cleanup of this Keltor Chemical Works Superfund sites. So I just popped it into the end of this PowerPoint so you can see sort of how these agencies communicate about these sorts of projects. They give you a nice timeline of, hey, the site was in operation here, soil gets contaminated here, all right, gets added to the national priorities list, not national projects list. Sorry, it's the NPL is the priorities list. Okay, 83, 2003, it gets deleted. Then they deleted. They discover that there was more contamination. An additional investigation gets initiated. They go out there, they sample, they characterize, they see how bioavailable the waste is, all right? More analysis, human health risk analyses, boom, 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 boom. All this stuff. Long, drawn-out process. 2023, cleanup action, all right? Initial contamination, 60s to 80s. 2023, cleanup action, all right? Takes a lot of work, takes a lot of steps, everything needs to be characterized. You have to demonstrate how hazardous this is. With the Superfund becoming a lower and lower pool of money, getting the project to actually be conducted becomes more challenging because you're competing with other Superfund sites or national priority list sites for the funds. So you have to say, ours is more dangerous, ours is more hazardous. Okay, so what's going on? Here's this big gravel bar. Here's where the mill was, okay? Check this out. There's a pasture here, the mill, the gravel bar, okay? Flood happens. It disperses all this contaminated soil into the pasture. They identify health risks. Bunch of, you get action from all of these different regulatory agencies. It's a historic site. It needs to be preserved. Can we do the project? Okay, there are endangered species present. Can we do the restoration project while still maintaining protections for those endangered species? Where are we going to get funds for this? Well, the Clean Water Act is going to allow us to justify this project. So much going on. All these different groups, all these different agencies involved in this project. All right? Yeah, so yeah, you're on the same page. Hey, look at all these people that you're talking to right here. All right? Very good. Very good. Cooperative agreement gets entered into. Oh, people go there. This is an EPA presentation. I'm not taking responsibility for how they structured it, but this is the information they're presenting. Look, contamination, human health risks. All right, people harvesting the fish, the mine tailings, the impacted soils. All right, bad stuff. So I just want to really get down to, here's the uses, the tribal uses of the area. All right. There's also recreational uses, of course. Very good, very good, very good. Children playing there. TEK. They tried to implement some TEK practices in how they did this project, specifically in the restoration using native plants. All right, so that after they had done the removal of material, they could put soil in there that would foster the growth of native plants. Seems like, for all intents and purposes, a pretty good restoration project. They pulled out a bunch of soil, they did the dig and dump method, is what they call it, where you dig up the contaminated soil and then you haul it someplace else and you do off-site disposal and you dump it. All right? Then you put new soil in there. Here's some pictures, of the project area. They got these to prevent prevent loss of material. They're pumping water and doing all this cool stuff. Okay? Look at that project. Yeah. Oh yeah. This is a really cool piece of equipment. This is, of course, what I'm like, oh, what's this? What's this little gun that this person's pointing at the soil? It's an X-ray fluorescence meter, and it's really cool to be in as the technology has improved to the point where you can more quickly assess whether you've gotten the contaminated soil out. You can detect trace amounts of heavy metals and other contaminants just by going boop and pointing, shooting a little gun at the soil. It's really nice. You blast it with X-rays, and then it re-radiates other wavelengths of radiation, and then you can use that to determine concentrations of contaminants. Yeah.
You get sick from that? Like those
from the X-ray fluorescence machine? I mean, if you were blasting it at yourself, yeah, you totally could. Because X-rays are high energy enough that they can get through your tissue and impact your genetic material, and they become mutagenic. Yeah. So you just watch where you're pointing this darn thing. Yeah, good stuff. Anyway, they did this project. There were a lot of steps to it. I don't have a ton of details. I'm not an expert in this project either, but I just thought it would be reasonable to show you, look, here's a Superfund project that was conducted in this area. Yeah, please.
So for a lot of Superfund cleanups, is there often a lot of incidents of people getting sick from it or getting contaminated?
During the cleanup stages?
Yeah.
That is supposed to be controlled for. I don't know of any case studies, but you can rest assured that has occurred. Absolutely. Yeah. Do you have a good example of that?
Why is Tuluwa not on the list? Tuluwa, the island in the bay.
Oh.
The Weehawk creation.
As in the national priorities list, it was a Superfund.
Before it was cleaned. Well, it was a community project, though. It was community cleanup.
Oh, so Superfund wasn't used for it.
Right.
Then that's why, because these are just Superfund sites. Yeah. No, and this is...
Relative to what's funding it.
Yes, exactly. The Superfund itself is meant to be this big... The idea of how I was structuring the hazardous waste disposal thing, it was supposed to flow like this, where people generate hazardous wastes. We can't always hold the people who generate those hazardous wastes accountable. There's been a federal effort to create this big fund of money used to clean up those sites, regardless of whether money could be recovered from the creators of the waste. And then these Superfund sites are examples of that. So that's why it's not in this list of areas that have experienced heavy pollution or have had community projects done to clean them up. Yeah. Because rest assured, so many sites don't even get onto the Superfund list. It has to be demonstrated that it presents a very significant health hazard, health risk, and that there's no other way to take care of it, essentially. So community outreach, all this stuff. Anyways, there's a lot of slides here. I'm not gonna do the entire presentation because I didn't create it. But I just wanted to point out, hey, here's a project. Here's how the EPA talked about it. Yeah, and they were focusing a lot on how they were interacting with the Hoopa area and the people there. Okay. Good stuff. Thank you. Let's go ahead and get into the PowerPoint here. This shouldn't say week 12, this should say week 14. There, now it's like it never even happened. I know, incredible, right? Hopefully Man, these PowerPoints, they're covered usually in red text when I'm making them of like, John, remove this, change this, use the source in this file on your computer. I'm always afraid that I'm going to accidentally upload that. So like, John, stop taking so long. Go faster, fast through this. Anyway, we'll see. Agriculture and soils, all right? Just like how we do all of our different talks about, doesn't that look wholesome? Yeah. Just in the same way that we do all of our new topics, I'm going to first discuss basic terminology so we can understand the field the field of study that focuses on this stuff. What I'm telling you is we're going to talk about soils. Okay? Soils, what are they? We've got major problems with soil depletion, soil erosion, soil management. Okay? So a soil itself is a renewable resource, but we have, like with most renewable resources, we tend to deplete them more rapidly than they are renewed. Pretty standard, okay? How do soils get depleted by modern agriculture? All right, erosion, removal of organic material, removal of nutrients through overfertilization, single crops, monocropping, that's a huge issue. They remove certain things, and then you remove all of this organic material. When we say organic material removal, it's not like they are going into the soil and saying, oh, there's organic material in here, and they're pulling it out and collecting it. It's more that you've got all these resources in the soil, a plant grows, and normally it would die, and then everything would return into the soil, and that's great, that's the natural system. But if you grow something up, all right, and then you take it away, well, the things inside of that plant, inside of that organic material, are now gone from the system. Pretty standard issue, right? So what makes a soil? Soil is just wet. A soil, in general, includes both abiotic and biotic components, so living and non-living components, all right? Abiotic being the non-living component. So that's what we're talking about when we say a physical matrix here. It's a bunch of weathered mineral particles. It's rocks that get broken down into little tiny rocks, okay? Things where nothing's growing inside of them, really. Little particles where all the important interactions are occurring on the surfaces, all right? And I've talked to you about surface area to volume ratios before. Surface area to volume ratios are really important in this context as well. So the solid physical matrix mineral particles, they all get broken down based on these size classes. So we have these different official size classes for the particles within a soil. A clay, silt, sand, and gravel particle, these are all defined terms, all right? And they all relate to size. And when you're characterizing a soil's texture, which is incredibly important in how things can live in it, and in how water is held in it, and how water moves through it, all right? When you're characterizing a soil's texture, you are describing which proportion of the particles are represented by each of these size classes. Is it mainly tiny little clay particles? Well, then it's a clay. Is it mainly large sand particles? Well, then it's a sand. Is it mainly silt particles? Well, then it's a silty soil. Usually we talk about a loamy soil, but there's usually a combination of silt, clay, and sand. So you'll hear phrases like, it's a silty sand, or it's a silty clay, or, that's what they're talking about. And when you purchase a bag of gravel, that gravel is made up of particles between 2 and 75 millimeters. It's a pretty big size range, okay? Cool. So we've got the solid phase of slowly degrading particles, mineral particles. Then we've got organic matter in various stages of decomposition. So this is dead detritus that has gotten into the soil, leaf material, stuff like that, dead root material, dead bugs and worms and things like that, okay? All this organic material that's slowly decaying in the soil. and we call that humus, okay? Organic matter in varying states of decay. Now, technically, for humus to be the category, it should be sort of homogenized. So it's broken down to the point where you can't be like, oh, look, a leaf, and oh, look, a dead spider. It's more like just a mass of decaying organic material, which breaks down much more rapidly than these mineral particles, and which plays different roles in the soil, and which has energy in it that can be accessed. It'll decompose. When it decomposes, it'll release greenhouse gases into the atmosphere. So organic matter plays a very different role in the soil than these mineral particles. Okay? Living things in the soil alter physical and chemical properties of the soil. Well, what examples can you think of? Yeah. Root structures in like soil stabilization, maybe? Awesome. I love it. Soil stabilization, creation of macropores as they tunnel through. I'm stealing all of the good ideas off of that. Awesome. Who else has a way? Yeah, please.
Like legumes and soybeans and stuff that have a fungal association with nitrogen fixing?
Yeah. So I'm going to be a jerk and tell you that's usually bacterial, all right? It's usually a bacterium or an algae that's carrying out the nitrogen fixation, but a mycorrhizal association can enhance nitrogen-fixing symbioses, though there aren't any fungi that actually fix the nitrogen themselves. But 100% great. Nitrogen-fixing organisms, huge important aspect, all right? Everything needs nitrogen because nitrogen is in your genetic material, and it's also in proteins that make up the majority of your dry weight, all right? This is actually why have I done this before? I got all excited and I was like, this is why we have the flavor profile of umami. Did we talk about that? No? Oh, cool. Well, hey, it's fresh, you know? I talk about it in a lot of classes. Whenever I talk about nitrogen and nitrogen needs. Our bodies have ways of detecting that we're eating the things that we need, right? And then we've evolved to eat more of those things and appreciate those flavors. Umami is a more recently discovered and understood flavor profile, and what triggers it is the breakdown products of proteins, all right? So that's your body going, oh, I taste protein in this, that's good, I need that. Why do you need that? Because it has amino acids and nitrogen, which your body can then use to build up other proteins as you grow and develop. It's all about protein detection. And that's where that nitrogen requirement that's so important in the soil really comes from. It's all protein-based life, you know? Yeah, I love it. Nitrogen-fixing organisms. Yeah. Absolutely.
Carbon or nitrogen in the atmosphere, and then the whole system would get asphyxiated.
Yeah. The fungi are such good decomposers, better than bacterial decomposers, that without them, the rate of decomposition would be way too low. Detritus would accumulate, like you said. Everything would get locked into the system.
Which is exactly what happened when trees first invented lignin in the coal fields of Russia.
They didn't know. Yeah, they didn't know how to break it down yet. Yeah, so you couldn't break down wood, and then the majority of the tree just sits there. Yeah, it's super interesting. I absolutely love it. Yeah.
Mycelium and the fungi and the relationship with nitrogen availability for soil 260.
Oh, awesome. Oh, you're in soil 260 right now. That's great. I took that class back in the day. I liked it a lot. In fact, a lot of this material for our soils talk, I used my notes from soil 260 because I saved all my notes. Hey, what do living things in the soil do? Here's some examples that I put down. Removing water, adding organic matter, forming channels, alteration of chemistry via metabolism, deposition of waste products, etc. Nitrogen fixation, thank you for bringing it up. It's a good one. All right. Good. Oh, this is just fun. Soil and dirt. Soil and dirt are technical terms. They're usually just used synonymously. But a soil exists where it was formed, where dirt is soil that's been removed from where it was formed. So once you put a shovel into some soil and put it in a wheelbarrow and wheel it away, now it's dirt. Isn't that interesting? So you don't really buy a bag of potting soil, you're buying a bag of potting dirt.
Potting soil isn't soil. It's all organic.
It's all organic matter, yeah.
There's no clay or silt or sand.
Yeah, it's like a soil amendment. Yeah, more than anything. But you just put plants directly in it. It's wild. Yeah. Absolutely. Eat it up. What do soils do? Okay. Soils support plant growth, store water, recycle waste materials, modify the atmosphere. Things live in the soil, all right? And then in any soils class, they always point out it's also an engineering medium. You build a big pile of it, and then you build stuff on top of it. Cool? Or you block water movement with it. Good soil structure is usually considered half solid, half space, all right? And then half of that space in the soil should be filled with water, okay? And half of it should be open space for air. And these values change all the time. This is, of course, a very generalized ideal soil composition going on right here. And of that solid phase, there's going to be a little bit of organic matter and a lot of mineral particles, okay? Issue in soils is compaction, major problem, okay? You compact a soil, you reduce the amount of pore space, you reduce the amount of air it can hold, and you reduce the amount of water it can hold, all right? Soils need air. They need air because there's not photosynthesis occurring under the ground. So what processes are there for energy transformations? Well, they're all respiration processes, right? So you need there to be oxygen available, or at least some gases available for more complex types of breakdown. Question?
Wait, so for dirt and soil,
Yeah.
if you move the dirt and put it back if you put it back into the ground, it's soil again.
You put it back into the ground and then let it form for a while. So you let it take time to change and have some organisms live in it for a while and modify it. So it's all about where it formed.
Okay.
Yeah.
Oh.
Does that make sense?
Yeah.
But then, where's the time frame? Like, if I put it there for a week, is it now a soil?
I think most everyday people just call everything dirt. They
Yeah.
They don't say soil really.
Yeah. The bag, it says it, yeah. Yeah. It's just a little fun aside because I always like these technical terms that just make it into common usage, and we're just like, yeah. It is kind of helpful to be able to use those two terms for different things, because a soil that is still where it formed has the organisms that are native to the area and that have been that has a similar chemistry to the surrounding soils. And older soils, they're going to be, soils in their communities sort of co-develop. So it's going to be better probably, hopefully, at fostering growth there. Anyway, ideal soil composition, half solid, half gas, half space. Some of that space should be filled with water. All right, soil textures. I'm never gonna make you do a soil texture pyramid thing or anything like that. But what I wanted to point out here is the terminology for soil textures. It's all based around those particle sizes, right? Sand, silt, clay. Usually in a soil, you have a mixture of different particle sizes. So you'll call something like a sandy clay, all right? Or a silty clay loam, or a sandy clay loam. Loam is a term used to describe the ideal soil particle distribution to support plant growth, the size distribution. So loamy soils are balanced, they're ideal for supporting plant growth. You'll hear the phrase loamy thrown around sometimes, or it's common. I've seen it in a couple books, and like, it was a loamy field, So loam in a soil context just refers to fostering, having the correct particle size distribution to foster plant growth. And it's usually a balance of like 20% clay and then 40-40 sand and silt. Yeah. Now, why is soil texture so important? Soil texture is so important because of moisture retention, all right? Moisture retention and nutrient retention. And it all comes down to the surface area. Something I threw out there really quickly was just, hey, with a particle, a mineral particle, all the reactions are occurring on the surface, like the breakdown processes, and where does water get held on a rock? Water is held on the surface of the little tiny mineral particle. It doesn't absorb into the little mineral particle. So more surface area means more area to stick water onto. All right, so do I have a good, this'll work for it. Yeah, we'll get right to it in just a second. I'll draw on the board. That's always fun. So here's a little mineral particle. Here's a big mineral particle. So here's a sand particle. Here's a clay particle. All right. Water adheres to the surface of the particle. So while that sand particle right here has more total surface area where water could stick to, right? This clay, you can fit more clay particles in the same amount of volume, and therefore there's going to be more total surface area because this small particle has a higher surface area to volume ratio, and this sand particle here has a lower surface area to volume ratio. And the force that holds the water in the soil is right here between the surface of the soil particle, all right, and the surrounding water molecules. So here's the thing. When you have a bunch of these small particles, you can hold more water in the soil more tightly, but it can actually be too tight. So a clay can get really waterlogged and water won't drain out of it, and there aren't these big macro pores between the particles, so it can be an issue. All right? The opposite is true with the clay, with the sandy soils, right? With too much sand, the water drains out really rapidly because there's not as much surface area to hold the water to stick the water to. So you can see this. If you take a wet ball of clay and you lift it up, it just holds a bunch of water in it. You know, it takes a lot of energy to press that water out. But you hold up a handful of wet sand and water's dripping out of it constantly. Intuitively, you're aware of this. It's all about the surface area to volume ratios of the particles within that soil. Okay, let's talk about soil formation factors real quick. This is the CLORPT functional model. It's not meant to actually predict a value. So in these functional models, you're not supposed to put a number in for all of these different variables. What this is actually saying is just soil structure is a function of climate, organisms, relief, parent material, and topography. Okay? So there's no actual number of, you don't calculate a soiled S value of like 8. Yes, please. Yeah, relief is the direction that the slope is facing. Yeah. So it's like basically exposure to solar radiation. Yep. Yeah, with relief and topography. I'm sorry. T is not topography. I do this every time. T is time. All right? So relief is mainly, it doesn't really include all of topography because it's on a small scale, right? Because the soil at different, if you look at the overall topography, then what this model's meant to show, and it's good to clarify this. What this model's meant to show, right, is that if you've got a big mountain range, okay, this soil is forming differently than this soil is forming differently than this soil is forming differently than this soil, right? So that means that something is different about the relief. So relief is the term they use instead of topography, and it focuses on the degree of the slope and the face, which direction it faces. Yeah.
Kind of make material look like its own category.
Oh yeah, there's no M in there. Yeah. What? Chlorpum. Yeah, and you could always throw more into this. You totally can with functional models like this. And if you've got if you find a journal that doesn't care, you can publish another soil formation factor functional model, no problem. You know. Great. So check it out. Two soils that start the same can become very different based on, two soils can become very different if they're in different climates, if there are different organisms present, if they have a different relief, or if they're at a different location within the topography, if their parent material is different, all right, and if the soil has been around longer. So soils change over time. That's what this functional model's meant to illustrate. And one value of functional models like this is it's just like when you take an equation and there's one variable that you can't figure out the value for, right? You get it alone on one side and then you solve for it. You know what I'm trying to say? I'm trying to visualize there with you there. Okay, cool. If you can hold all of these other variables constant, let's say you want to determine the effect of climate on soil formation. Well, then in that case, what you need to do is find two soils that have the same organisms, the same relief, the same parent material, and have existed for the same amount of time, but are in different climates. That's how you have to carry out the study. To investigate the effect of one of these variables alone, you have to hold the other variables constant. All right, just an idea. And next time you see a functional model, just think about it. Think about hey, could I do a study where I held all but one of these variables constant to see the effect of it? Okay, good. Great. It's too much text. It's just too much text. I've already verbalized, I think, all of this. Soil texture is the most important characteristic of soils. You could argue that there are other important characteristics of soils, but soil texture is very important in determining water holding capacities, how water and nutrients move through a soil, and we're really concerned about that. Okay, great. I'm gonna keep on rocking forward. There's this slide I've got right here about soils and water. Okay, it's gonna start to move us into our water discussion. Great, we're doing great. Timing is perfect. Okay, water, how does it move through a system, all right? Let's start with precipitation. Water falls onto the soil. Some of it infiltrates, and then some of it runs off, right? The water infiltrates, eventually it reaches an impermeable horizon, okay? And then it just kind of flows out of that, and it flows towards these bodies of water. It moves away from it moves eventually into standing surface water, and then it leaves the system, okay? Or maybe it gets consumed too quickly or doesn't fall in appreciable amounts, so it never really flows away. It just drains a little bit, infiltrates and drains, and then gets taken up by plants. So water, what's its fate when it enters into one of these systems? It gets into the soil, some of it evaporates off of the surface of that soil or from the surface levels of that soil, and some of it is transpired by plants, where the water is taken up by the plant through its root system and then is lost through the leaf surfaces from the stomata. Did we talk about stomata at all? I don't really think we did. It doesn't really fit into our coursework perfectly, but if you take a bio course, they'll hopefully talk to you about it. Great. So water moves out through plants. That's a process of transpiration, okay? And evaporation and transpiration are two of the important ways in which water leaves the system. So we usually pool those terms into the phrase of evapotranspiration, which is sometimes used as a measure of how much water is being lost from a soil. And you'll see it if you look at any papers that have to do with supplemental irrigation, because what they usually do is you determine through an equation and through weather monitoring systems what the evapotranspiration rate was for a given period of time. Like for the last week, the evapotranspiration rate. How many millimeters of water did we lose? Okay? You get that value based on a big equation, and then you irrigate at a replacement ET, or you replace the water that was lost through evapotranspiration, keeping constant water levels in the soil. Different crops have different replacement evapotranspiration rates that you should irrigate at. Some plants, it's like irrigate at 80% replacement of the evapotranspiration over the previous 3 days. And this is how you can see an automation start to form in farming and in determining irrigation rates. And you can also see how you can do a more balanced type of irrigation, where what you're trying to replace is how much water evaporates out and is used by plants. You don't want to replace surface runoff water and evaporation water, because over-irrigation leads to all of this other water flowing out of the system. Anyway, I'm getting a little off topic, but that's what we do in this course, okay? I get off topic. That's the whole thing. Good. The surface area of the soil particles, as I mentioned previously, that's where the water is sticking. That's where the nutrients are sticking. There are nutrients suspended in the water, and there are also, these soil particles tend to have some regions of charge on them, meaning that charged soil nutrients that exist in ionic forms, can stick directly to the particles as well. So you got these two things. You got macropores and you got micropores. Macropores are really big, okay? Do I have another image? Nope. Macropores are big, micropores are little. If you have a bunch of little tiny clay particles, well then they all pack really tightly together. Think about a little bucket full of BBs. There aren't as many large pore spaces between each BB, okay? Think about a bucket full of marbles or a bucket full of ping pong balls, and there are all these macropores, these big pore spaces, all right, where water can really rapidly just drain by the force of gravity. So micropores are more prevalent in soils that have smaller particle sizes in them. Macropores are more prevalent in soils that have larger particle sizes in them. And macropores don't hold water very well. They give you a lot of pore space and a lot of gas, okay? But actually, if you take the total amount of pore space in a clay and add it all together, if you add together all of the micropores and see how much pore space there is, there's actually more pore space in a volume of clay than there is in a volume of sand, which is super counterintuitive, right? But think about a bucket full of these particles. A ton of the volume of that bucket is made up of this portion, the inside of the particle, right? More of the volume is taken up by particles. There's not as many intersections or external space. So while a soil made up of very large particles has many macropores, a soil made up of many small particles has so much micropore space that if you pool it all together, you end up with more total pore space. And the real question is, now you've got water there, can the plants actually access it? And that's where we'll get to next Monday when we come back for class, all right? And then next week, we got 140 slides. We can do it in 3 lectures. I think it'll be fine. Yeah, it's going to be a lot of fun. So thank you, everybody. We're just going to get through agriculture and water. There's no way we're going to have time for the energy lecture. Apologies, everything we talk about here, all these topics are just so darn important. It's really hard to continue to whittle them down. But thank you. You made it through a lot of ESM 105. One more week, 3 more days, and just get those annotated bibliographies in, get them off your plate. Anyways, that's it, everybody.